Hey, my name's Zach, and I'll be talking about my paper separating words in trace reconstruction. So let me give first quickly an outline of the talk. So the first 12 minutes will be about trace reconstruction, and the last 12 minutes will be about the separating words problem. And throughout the talk, we omit constants and logs just for simplicity. Okay, so let's talk about the trace reconstruction problem. So you take a string x, 0, 1 to the n, and we define a trace of x. It's a random string, and it's obtained by deleting each bit with probability of x with probability 1/2 and concatenating the result. So here's an example of x and a random trace. So x will be 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1. And the randomness is such that the first bit is deleted, the second and third are kept, the fourth is deleted, etc. And then all that's outputted is this final string right here. So in particular, we lose the information about where these bits came from in the initial string. All we see is the final trace. Okay, so now let me say what the trace reconstruction problem is. So there's an unknown string x of length n, and the question is how many independently drawn traces of x do we need so that we can determine x with probability at least 0.9. So let me just explain how it works. So let's say x is the unknown string, 0, 1, 0, 1, 1, 0, 1. It's unknown. And here's an example of taking 5 independently drawn traces. So the first trace, like the first, third, and fifth bits are deleted, and then all that's outputted is 1, 1, 0, 1, etc. This happens 4 more times. And so this is all behind the scenes. This is the unknown string, and all we see is these list of traces, 1, 1, 0, 1, 0, 1, 1, etc. And we want to be able to guess this string, this unknown string, from just looking at these strings. So note that if we, no matter how many traces we take, there's always some probability that all of the traces are just the empty string because of deleting all the bits. So it's not true that the traces always give enough information to determine the unknown string, but we want with probability at least 0.9 that they do. And we want this answer for the worst case x. Yeah, since x is unknown, it wouldn't even make sense for a fixed x. So yeah, just, okay. So the optimal algorithm is actually quite obvious. You choose the x that most likely generated the observed traces. And the fact that this is optimal, it holds in a much more general hypothesis testing setting. But the issue is that we're not able to analyze this algorithm. So we instead come up with worse algorithms. Okay, now let me talk about bounds on the problem. So an upper bound is e to the n, and a lower bound is n. So for the proof for the upper bound, we can just wait until we see the whole string, right? Like if we take like a trillion to the n traces, then with probability at least 0.9, we're going to see the whole string. And we know what n is, so we know when we see the full string. If you don't know n, you can just deduce it from the traces by multiplying the average length by 2. Anyways, so the upper bound is very trivial. We can just wait until we see the whole string. For the lower bound of n, you consider this pair. So it's all zeros except for a 1 basically in the middle. And I won't go over the proof, but this requires n because basically the only information you have is where the 1 occurs. And it comes down to distinguishing between 2 very closely related binomial distributions. And the main question is whether polynomially many traces suffice. Okay, so the trace reconstruction problem is essentially equivalent to its pairwise version. So if the unknown string is correctly promised to either be a certain x or y, then how many traces are needed to determine the truth with high probability? So instead of an arbitrary unknown string, we know it's unknown, but we know it's guaranteed to be either a certain x or y. It's guaranteed to be one of 2 things. And we want the answer for the worst case pair x comma y. So the equivalence is not too hard to see, but we won't go over it. Okay, so let's go over an example. So how many traces are needed to distinguish between these 2 pairs? So if you're watching on YouTube, you could pause to think about it if you want, but so the answer is actually a constant suffices. So the idea is just to look at the first bit. So if the true string is this top one, 0, 1, 0, 1, dot, 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 then the probability that the first bit is a 0 is 1/2 because we could keep the first bit. Or if the first bit being 0 comes from this bit, the third one, the probability of that is 1/8, etc. So If the true string is this top one, then the probability that the first bit is a 0 is 1/2 plus 1/8 plus 1/32 plus etc., which is roughly 2/3. And if the true string is this one, then the probability that the first bit is 0 is 1/4 plus 1/16 plus 1 over whatever comes next, etc., which is roughly 1/3. So the point is, the algorithm is as follows. You get a bunch of traces. You just look at the first bit. And if roughly 2/3 of the first bit are 0, then you guess the top string. And if roughly 1/3 of the first bits are 0, then you guess the bottom string. And with high probability, like, will be correct. Okay, so a question you could ask is like, what happens if we always just focus only on the first bit? Like, can this strategy always work? And the answer is no. So for example, you can go back to that thing the example that required n traces, right? If you consider this pair, then like with insanely high probability, the first bit is a 0. So yeah, there's only an exponentially small difference in the probability of seeing a 0 as the first bit. So that means that exponentially many traces are required if we do the strategy of only looking at the first bit. But going back to this example, let's say the 1 is at index n/2 and n/2 plus 1. Then we can focus on the n/4th bit. So what I mean by that is that the probability of seeing a 1 at index n/4, if the true string is the top one, is about n⁻³ greater additively than if the true string were the bottom one. So the point is that we see all these traces. We just look at the n/4th bit. We count the proportion of the traces that have a 1 there. And the point is that the probability, if it was the top string, would differ from the probability if it was the bottom string additively by at least n⁻³ So that means that n⁻³ traces suffice. And what simultaneous work of D'O'Donnell-Servideo and of Nazarov and Perez showed is that there is always at least some bit that we can focus on. So what do I mean by this? So their theorem, proven in 2016, is that for any distinct x and y in 0, 1 to the n, there is some index j, so that the probability that the jth bit of the trace is a 1 differs by at least e⁻⁻⁴n. So what this means is that we just, once again, we get all the traces, we only look at the jth bit, count the proportion of those that are 1, and yeah, we should be able to determine the true string based off that proportion, because with high probability, I mean, these proportions have different expected values. They differ by at least e⁻⁻⁴n. So therefore, e⁻⁻n traces suffice for trace reconstruction. And the proof uses complex analysis, which is pretty cool. We don't have time for it though. In 2018, Holden and Lyons proved that n⁵ traces are required by considering this pair. So it's the same pair as the one that gave n as a lower bound, except instead of having the 1 in the middle be padded with zeros, we pad it with 0 1s. So like there's this one where we don't know where it is and it's padded with 0 1s. Okay, so the first batch of bounds were e⁻n and n, and the second batch of bounds were e⁻³ and n⁵. So still a huge gap. In 2019, we improved the lower bound to n⁵ by painfully, carefully analyzing the same pair that Holden and Lyons used. So the same exact pair, they showed that n⁵ are required. We showed that n⁵ are required. And that is tight for this pair. So this pair can be distinguished into the 3/2. Okay, and in 2020, nearly simultaneous work of Chen, De, Lee, Servideo, Sinha, and Narayanan Ren published the observation that for a given small w, small string w, few traces suffice to determine how many times w appears as a contiguous substring in the unknown x. So by contiguous substring, I just mean like, yeah, a contiguous substring. Okay, so for w equals 1, this fact is quite obvious. So multiplying the number of 1s that appear in the trace by 2 gives a good approximation to the number of 1s in x. Yeah, just because of how stuff works. So you can determine the number of ones in the unknown string by just looking at the number of ones in the traces. But okay, let's say we wanted to determine how many times 0, 1 appears as a contiguous substring in the unknown x. This is much harder. So what one does is a weighted count of 0, 1 pairs in the trace, with the 0 occurring before the 1. So here's the scary formula. You look at pairs J0 and J1, with J0 less than J1, such that the trace denoted by U, the J0th bit is 0, J1st bit is 1, and you weight by -1 to the gap. It's not too important to understand this. The point is that the right-hand side, it counts the number of times 0, 1 appears as a contiguous substring in X, and we can figure that out just by looking at the traces. Okay, so what the Deodano Cerverio and Nazaro Perez proofs of e to the cube root of n did was get an approximation to the weighted count of the number of ones in X, with the weights being based on the positions of the ones. So specifically, they use this formula. So what you should focus on for this formula is that this thing that appears in the expectation is just something about the traces. It's just a quantity involving the traces. And the right-hand side is a weighted count of the number of ones, where you weight by the position of the one. So instead of getting an approximation to the number of times that W appears in X, we instead get an approximation to a weighted count of the number of times that W appears in X. So for example, if W equals 0, 1, we use this. So once again, this thing in brackets is something scary, but it's just something based on the traces. And the point of it is that this output gets a weighted count of the number of time of the, like a weighted count of 0, 1 contiguous substring appearances. Okay, and by doing some complex analysis, building off the work of Borwein, Erdely, and Kos, we can then improve the upper bound to e to the 5th root of n. So our main theorem is that e to the 5th root of n traces suffice for trace reconstruction. Okay, so to summarize, the final batch of bounds is an upper bound of e to the 5th root of n and a lower bound of n to the 3/2. And more work needs to be done. Okay, so now let's talk about the separating words problem. So deterministic finite automata are the object to study, and it's one of the most basic computational devices. So here's an example of a DFA. So you have a bunch of states, Q0, Q1, Q2, Q3, and Q4. You have a start state, which is Q0, and you have accept states, which are, in this example, are Q3 and Q4. And the DFA takes as an input a string X and 0, 1 to the n. And it starts off at Q0 and then goes through the bits, bits of X 1 bit at a time, and moves according to the arrows. And we say that the DFA accepts X if the state that we end up at is an accept state. So in this example, Q3 or Q4. Okay, so telling two strings apart. As Jeffrey Shalit says in one of his slides about the problem, it's one of the most basic computational tasks for one of the most basic computational devices. Okay, so we say, okay, so let's do some examples. So this DFA accepts the string 0, 0, because if you start off at Q0 and then go 0 and then go 0 again, you end up at Q3, which is accept state. For 1, 1, 1, you can go 1, then 1, then 1, and you end up at Q4, which is an accept state. And you can check that 1, 0, 1, 0, 0, 1, 1 is accepted. And it rejects the string 0 because you end up at Q1, which is not an accept state. It rejects the string 1, 0 because you end up at Q1, which is not an accept state. And 1, 1, 0, 0, 1 ends up at Q2, which is not an accept state. And we say that a DFA separates two strings X and Y if it accepts one but not the other. So for example, the above DFA separates 0, 0 and 1, 0, since it accepts 0, 0 and rejects 1, 0. So the separating words problem asks for the minimum number of states a DFA needs to separate two distinct strings, X and Y and 0, 1 to the n. And we asked this question for the worst case pair X and Y, so the answer is just a function of n. And we restricted to strings of the same length just because if they have different lengths, then it's easy. So in 1986, Goralczyk and Quebec showed that any distinct X and Y, 0, 1 to the n, can be separated by a DFA with a sublinear number of states. And they also showed a lower bound of log n. So there exist x and y for which no DFA with fewer than log n states can separate. And the example giving this lower bound of a log n is for, so you set k to be log n, and you look at the string 0 to the k, 1 to the k plus LCM of 1 through k, and 0 to the k plus LCM of 1 through k, 1 to the k. So the point is these two strings differ by you either have a batch of ones that's of length the LCM of 1 through k, or a batch of zeros that's of length LCM of 1 through k. And basically, because these batches are divisible by all small numbers, you can't distinguish with a DFA fewer than log n states just by a periodicity argument. Okay, Robson then came up with a clever argument for improving the upper bound. He proved that any distinct x and y can be separated by a DFA with n to the 2/5 states. And this bound was stagnant for 31 years, and we recently improved the n to the 2/5 and n to the 1/3. Okay, so let's go over a proof of an n to the 1/2 upper bound first. This will contain the ideas that we generalized to get n to the 1/3. This proof has been found a couple of times. Okay, so the idea is to count modulo q, the number of ones in positions that are congruent to I mod p for some I, p, and q. So you have your string x, and you look at positions that are I mod p, and you count the number of ones that you see, and then you reduce that count modulo q. And we can do this with pq states. So we can have the states be z mod p cross z mod q. Well, states be the elements of z mod p cross z mod q. And what we do is we keep increasing by 1 mod p at each input. And we add 1 to the counter, which is z mod q, each time a 1 is read when we're at an index that is I mod p. So here's an example with p equals 5, I equals 2, and q equals 2. So the point is that you you have 2 copies of z mod p. And as the arrows show, you just cycle between them, except you switch to the other level, which is the same as adding 1 mod 2, if when you're at an index I mod p, i.e. when you're at an index 2 mod 5, if you read a 1, then you go to the other level because that's equivalent to adding 1 to the counter, and vice versa if you're on the top level. So if you didn't follow the details, all we're doing is counting the number of ones and positions that are I mod p and reducing this count modulo q. So that's what this DFA counts. So take distinct x and y and 0, 1 to the n. Oh, I guess, okay, so for this, I didn't say what the starting state is 0, 0, let's say, and we'll specify the accept state soon. Okay, so take the distinct x and y to the n, and let's just introduce some notation. So let a and b be the sets of indices where x is 1. So let a be the set of indices k, such that xk is 1, and b be the set of indices where y is 1. And for I and p, define AIP to be the elements of A that are I mod p, and BIP to be the elements of B that are, oh, sorry, this should be B congruent to I mod p. Okay, so the above idea can be rephrased as finding some I, p, and q with the size of AIP not being congruent to the size of BIP mod q. And the number of states we would need is PQ. So just to isolate this problem, we have this purely like number theoretic-ish problem. We have 2 distinct subsets of 1 through n, which like corresponds to the condition that x and y are distinct. And we want to find some I, p, and q with the number of things in A that are I mod p, not equaling the number of things that are in B that are I mod p modulo q. And we want this to happen with pq small. So the q isn't that important actually. So if we can find I and p so that the number of things in A that are I mod p is not equal to the number of things in B that are I mod p, then by basic number theory, we can find some q of logarithmic size with AIP not being congruent to BIP modulo q, right? Like if you have 2 numbers of size at most n and they're different, then you can't have all primes of size at most log n dividing both of them. Okay, so we come to the number theoretic problem. Let A and B be distinct subsets of 1 through n, and the question is how small of a p can we find so that there is some I with the size of AIP not equaling the size of BIP. So taking the negation, we're asking for the largest p so that there are 2 distinct subsets of 1 through n with the same number of evens, the same number of odds, the same number of things 0 mod 3, the same number of things 1 mod 3, the same number of things 2 mod 3, all the way until the same number of things p minus 1 mod p. So yeah, can we have two distinct sets with the same number evens, odd, etc., all the way up to things that are p minus 1 mod p? And the answer is root n. So in other words, for any distinct subsets a and b of 1 through n, there are some prime p at most root n and some I, so that the number of things in a that are I mod p does not equal the number of things in b that are I mod p. So I'll give the precise form here. It's big O root n log n, that's the upper bound. And okay, so let's go through the proof. It's a proof from the book. So suppose it's false. Then you look at this polynomial, the sum from k equals 1 up to n of the indicator function. You give the coefficient +1 if k is in a but not b, and -1 if k is in b but not a, and otherwise the coefficient is 0. So actually, if you remember our original setting with strings, this is basically like you sum over xk minus yk and multiply by z to the k. Okay, but the point is, so this is obviously a polynomial of degree at most n, just because it is. And under the assumption that the theorem is false, this polynomial has roots at each of the 2 pi I m over p for all m and z mod p and p at most root n log n. So the reason this is true is just because you can, if z is of the form is a pth root of unity, then you can divide the sum and you can split up the sum based on the congruence of k mod p, and you can work out the details. But the point is, we have this polynomial of degree at most n, and it has all these roots. And that means the polynomial must be identically 0, because if you just count the number of m and p such that, yeah, the number of m and p is greater than n. So this contradicts that a and b are distinct. Okay, so this gets a root n upper bound on the separating words problem. Okay, so what was our idea? Okay, so the idea we just implemented was to count the number of ones in positions congruent to I mod p. This can be phrased as counting the number of times 1 appears as a contiguous substring starting at an index that is congruent to I mod p. Right? I mean, so this equivalence is obvious. You'll see why I'm making the equivalence in a second, but it is just the same time counting the number of times 1 appears as a contiguous substring in x, and the starting point, the starting index of the appearance of this contiguous substring is at an index that is congruent to I mod p. Okay, so the reason of phrasing it like this is we can generalize this to counting the number of times a string w appears as a contiguous substring starting at an index that is congruent to I mod p. So here's an example. So suppose that x is the string 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, and that w is the string 0, 1, and p is 2, and I is 1. So we're looking at appearances of 0, 1 as a contiguous substring in x that start at an index that is congruent to 1 modulo 2. So here's an appearance of 0, 1, and it starts at index 1, which is congruent to 1 mod 2. Here's another appearance of 0, 1, but it starts at index 4, which is not congruent to 1 mod 2. And here's the last appearance of a 0, 1. It starts at index 7, which is congruent to 1 modulo 2. So the idea is, instead of looking at ones at position congruent to I mod p, we look at appearances of a certain string as a substring starting at an index I mod p. And we don't have time to explain how, but if we choose w wisely, we come to the following problem. First, we say that a subset of n is d-separated if all the distinct elements of it differ by at least d. So here's the problem. A and b are distinct n to the 1/3 separated sets, subsets of 1 through n. And we want how small of a p can we find so that there's some I with the number of things in A that are I mod p not equaling the number of things in B that are I mod p. So before, we just had, before the problem just had A and B distinct subsets. And the answer was n to the 1/2, like the square root of n. Here, we're requiring, we can assume that we're requiring that they're n to the 1/3 separated and asking if we can do better. So under this assumption that they're n to the 1/3 separated, can we find a smaller p? And note that such A and B have size at most n to the 2/3, so it's plausible that there's some prime p of at most square root of that size, in analogies to the square root of n we just said was the answer to the previous problem. So it's plausible that the answer is at most n to the 1/3. And our main theorem is an answer. So we proved that for any distinct n to the 1/3 separated subsets of 1 through n, there is some prime p, and if I'm being technical, it's some constant n to the 1/3 log to the, I forgot, I'll just say 10th of n to be safe, and some I with the number of things in A that are I mod p being different from the number of things in B that are I mod p. And we proved this by complex analysis, building off the work of Borwein, Erdely, and Koos. Okay, so let's summarize. So bounds on the separating words problem, the upper bound is n to the 1/3, and the lower bound is log n. So there's much more work to be done. Okay, thank you for listening.